Okay, so here we're going to talk about this equation, which is I equals NAVQ, and how we actually get to it. So what we can do is we can think about an electrical wire. So here's our electrical wire. And one thing we must bear in mind is the electrons are already in there. It's a really common misconception is that students will think that you've got this, the cell or the battery, and that somehow injects, it's like a little pipe, like the wires are little pipes carrying the electrons supplied by this. What these do is they make the electrons actually move by giving them electrical potential energy, okay? But the electrons are in the wire, they're contained within the wire. Now, it's not very useful for physicists or for engineers to think about an entire electrical wire when we're looking at this kind of stuff. So what we do is we imagine we just cut out a little bit of that wire. So we look at this cylinder. We look at the cylinder which has got some properties. For example, we know the cylinder has got a certain length. And we'll also know that it's got a certain radius r. Or you can think about the diameter as well, either way. And so what we can do from that is we can find the volume of that piece of cylinder, which is useful to us. I'll talk about that in a sec. But first of all, if you want to get the volume, so volume is just the area multiplied by the length. And the area, of course, is equal to pi r squared. So the volume is just pi r squared L. Fine. Okay. What we can also do is we can simplify that term just to A. And like I said before, that A we usually write with a capital. Okay? Anyway, we've got a volume of this, but why do we care? Well, scientists, when they study the materials, they can look at various different properties of materials. And if you're looking at electricity, what you're interested in is the free or conduction electrons, the ones which actually move whenever you have an electric current. What we're interested in is how many conduction electrons are there in a unit of area. And that lets us compare one material with the next. If you were to compare, for example, copper with, so imagine we had a cubic meter of copper. Just imagine that's a cubic meter. So there's copper and a cubic meter of plastic. Okay, so trans on similar sizes. PLA. Right, let's write that. We're going to get far more conduction electrons, not necessarily more electrons, but more free electrons which can move in a current in our copper than in our plastic, which is why copper is a much better conductor than plastic. We're more interested in it as electrical engineers. So this brings us then to this number n, the number density, and that is just the number of free conduction electrons per cubic meter. All right, number NO of free electrons per cubic meter. Now, I've talked about this and I've talked about the volume of this. So what we can do is we can use these two things to bring together to get the actual number of electrons. We're very rarely, or if ever, going to have a piece of electrical wire with a volume of 1 cubic meter. Okay, that'll be a huge amount of wire. Now, if we want the actual number of electrons, capital N, we just take the number per cubic meter and we multiply by the volume of the thing we're looking at. Okay, so we could write it like this: N equals N, the number density, multiplied by AL. Or we could say by pi r squared L or whatever, okay? Depends how we want to use the units, depends what units we're interested in, and also depends on what changes we're interested in. If we look at this in terms of changes of density, in terms of changes of the cross-sectional area of the wire, so that cross-sectional area being this area here. Let's just highlight that in pink, highlight them both in pink. There's the cross-sectional area. Then maybe we might start looking at A, not in terms of just the letter A, but in terms of pi r squared. Okay. Anyway, this gives us the actual number of electrons in that. And again, we're interested in that because it's the electrons which are going to move. Okay. So what we can then do is we can find the actual total charge that is in this. So we're looking at the number of charge which is inside this little cylindrical section of wire, okay? And to get that number of charge, well, we've got this, which is our number of electrons. So to get the total charge, big Q, which is in this, we take the number density multiplied by the area, cross-sectional area, multiplied by the length, multiplied by the charge of one electron. Because you remember, this NaL gives us the actual number of electrons. And to get the total charge, we just multiply that by the charge in coulombs of one electron. Should be simple enough, because we talked about this before. So this then will give us the total amount of charge inside this. Maybe it's not moving. We're not too worried about that just yet. But let's say that it is moving. Okay? If you remember, we need to look back at what does current actually mean. And as we mentioned before, current is the rate of flow of charges. So it's charges per second, okay? So it's coulombs per second, which is equal to an amp, okay? It's in the same way that a coulomb is equal to an amp second. You can see we've multiplied both sides by S to get to this, okay? So considering that, if it is the coulombs per second to get the current, well, what I can do is I divide this side by S to make this into current. But of course, if I'm following the rules of mathematics, which I am, I divide both sides by S. Sorry, let's call it T. T for time, because we use S for distances quite a lot. Okay, so I equals Q over T. We substitute that in. I equals number density multiplied by A multiplied by L. And if you remember, these together are equal to the number of electrons. And when I multiply this by Q, the fundamental charge, that gives me the total charge. Okay, so this is equal to big Q. And then, of course, I've divided both sides by T, so that's got to be divided by T still. So you can see here that all works. Current is the charge divided by time. Number of electrons multiplied by the fundamental charge to give me the total charge. So that's number of electrons multiplied by the charge of each electron to give me the total charge, and then divide by time. And of course, one thing we can also say, one way we can simplify this equation very nicely is that if I take distance and divide by time, then I get speed. So NaVQ, because these two cancel to make V. It should be a capital A. Let me write that neatly. I equals NaVQ, which is equal to big Q over T. You see why I'm using the two different Q's, of course, then, just to get less confused. Now, when we look at this V thing, really what that refers to, and you will see this term crop up, is this mean drift velocity. Because the thing is, if you imagine inside even the most perfect substance, electrons are going to be moving in different directions. So if you think about the inside of an electrical wire, so we had these magic eyes and we could see the atoms themselves. Okay, I know they're going to be closer together, but you know. So you imagine you've got this little electron moving this way. Well, if it gets closer to this one, then it's kind of going to start going this sort of way, and then it gets close to this one, so it's going to be repelled by the shells of the electrons. So they don't have any specific velocity. Okay, so we just kind of take the mean. It's not very useful for us to think about the velocity of one electron. So what we're thinking about is the mean drift velocity, like what is the average velocity of all those electrons. And of course, if we've got our potential difference between here and here, then the velocity is going to be on average in this direction. So we don't need to worry about the fact of this moving this way and this moving this way. Generally, any velocities that are at right angles to the actual potential difference will in sum cancel. Okay, so that is how we get to this equation. The task I'm going to give for you for tomorrow, or for today if you're watching this on Friday, involves this kind of stuff here. So, do I have a blank sheet of paper? Kind of blankish. Things to remember when you're solving a problem with this is just look at the data you might have. So any question you might have, let me see, number of electrons. And to get the total charge, you just multiply that, let's say total charge, or some total Q, or big Q, is equal to the number of electrons times little q. Okay. Top tip, remember, take your data. So let's say you get a question that says, okay, so you know the number density, and you know the radius, and you know the length, and you want to, and you're, let's say, and you also know the current. And let's say they ask you to find the mean drift velocity. You have enough information here. If you've got this, if you've got this, and this, and this, and you want to find this, you can get to it. So if you're trying to find the mean drift velocity, what I would next do is I'd write out the equation, I equals NAVQ. Now, of course, we don't know A, but we can get to it very easily because we know R. We know the radius. We want to find the cross-sectional area. What I'll do is I'll put in I, which I know equals N times pi R squared. Remember, maybe do that in brackets to help you so your order operations doesn't mess up, times V times Q. And of course, what you could then do is start dividing things out. I would solve this for A, and then comes back to I equals NAVQ, and then start dividing so you get this term by itself, the V term by itself. So divide by QAN, so V equals I over QAN. And that should get the mean drift velocity for you. Okay. Remember that these are typically very, very low. Electrons are incredibly small, but the actual drift velocity will be, they move very slowly. It's like sludge. One other thing as well, actually, let's just imagine, again, let's kind of imagine the circuit as we're just looking inside the wires, okay? And let's think about cause and effect. So what we've got here, we've got our source of potential difference, and we switch it on. Now this is what provides the push. So we imagine, okay, so it starts to push this electron. And what do electrons like to do to each other? Well, they also like to push each other. They repel one another because they've got like charges. And that message of repulsion happens at the speed of light. Okay, so you know if you push on something, it's going to move, right? And that thing moves because you're compressing its particles. These don't compress each other, obviously. As soon as this moves, it starts to compress the other one. So that is the highest, the largest speed that exists in the universe. And this is why it looks like it all begins instantaneously. When you switch a light on, it looks like the light comes on straight away. You switch on any electrical circuit, it looks like it comes on straight away because those messages are sent at the speed of light. Now that has to fade in because like they need to, well, they just fade in because the power sort of increases the way liquid crystal displays work. But just goes off like that, almost instantaneous. And if you can imagine, it's not actually doing this distance. It's not going from like shift to off to the screen. It's going much, much further because of all the little wires wired in together in the integrated circuit inside this. So anyway, because the message travels at the speed of light, that means effectively electricity travels at the speed of light. The electrons don't, but the actual message, the push, does happen at the speed of light.